Hi guys, please like, share and subscribe. And if you want full course for any actuarial subject, visit theactuarialguy.com or WhatsApp on this number. Thank you.
Okay, so at this point, I want to discuss the concept and the intuition behind hypothesis testing. Now, trust me when I say this is one of the most poorly understood topics, not in terms of solving exam questions, but simply in terms of the why behind how we do it, right? Where does it come from? What is the intuition? What is the logic? We will understand the idea of something called as the probability value, which is also called as p-value. This concept is asked a lot in interviews, right? And this is something which most people, while they apply it, they don't understand it. So because our focus is always intuition and first principles thinking, we'll get into the depth of this, that what does it even mean and why do we do it the way we do it. Okay, so now let's just start with this. I will go through this with an example. Okay, let's say there is a school or a university. Okay, let's start with a school. Okay, now what you want to do is, in this school, let's say there are a total of 5,000 students, right? And what you want to do ultimately is you want to test a hypothesis for this population. So this is my population. You want to test a hypothesis for this population. The null hypothesis is that the average height of students in this school, the average height represented by mu, is 170 centimeters. Okay. The alternative hypothesis in this case is that no students are taller than this. That is, the average height of the students in this school is more than 170 centimeters. Right? This is the hypothesis test that you're doing. So you're simply interested in knowing whether the average height of the students in this school is more than 170 or 170. This obviously is a one-tailed test, because you are only interested in greater than 170. You're just checking if they are taller than 170 or they are 170, right? You're not checking to the left of it. So that is something which is most important. Now let's just get into how do we do it. Okay, so now obviously when you want to check or test this hypothesis, you would not go to the entire school and take measure of everyone's height and then average it. That is tedious. Okay, so if you measure heights of all students, that is a tedious task. You would not do it. Okay, what you would do is you would pick a sample. Let's say you pick a sample of, let's say in this school, it's a small school, so there are let's say a total of 16 classrooms. Okay, so I'll just divide this into a 4x4 grid. So there are 16 classrooms. Okay, so 4x4 grid, 16 classrooms. Now what you would do is you would randomly pick two classrooms. Let's say you pick this one and then you pick this one. Okay, and these are your sample points. So you've randomly picked them, there is no bias. Okay, right? And let's say all the classrooms are expected to be identical. They are of the same grade, students of the same age are there, everything is the same, right? So you took this sample, and based on this sample, you want to know which one is true, whether the null hypothesis is true or we can reject the null hypothesis. So this is the decision that you want to make. Now let's say you know a couple of things. Okay, what is known? The first thing you know is that the standard deviation or the variance of the heights of students in this school is expected to be 900 centimeter square. So your population variance is known. Second, the sample you are drawing, the size of this sample, these two classes, is 40 plus 40, 80, let's say. So your n is equal to 80. Okay, this is what we are working with. So this is a large enough sample, right, for applying central limit theorem, right? The third thing that is known to you, that your x bar, when you take the average height of these students from these two classes, that is your sample mean, it comes out to be 190 centimeter. Okay, so now based on this, you want to check the hypothesis or test the hypothesis that can the population average height, that is the average height of the entire school, of all the students in the entire school, be 170 or it is more than 170, right? Now uh, based on uh, your intuition, what would you guess? Okay, take 2 minutes, think about it. If the sample height has come out to be 190, right, that is you took two classes of students, right, and you measured their height. Okay, that has come out to be 190. Is it possible that the height of the entire school, the average height of the entire school, is equal to 170, or do you expect that it will be higher than that? Okay, so your intuition would tell you. So one set of argument can be, okay, intuition 1 can be that, see, 190 is very high, right? So it's unlikely that the average height of the entire school is equal to 170, right? You would say, based on this sample, it doesn't seem like the average height of the entire school is 170, because these two classes are a representative sample of the entire school. So how can it be that the average height of the two classes is 190 if the average height of the entire school is just 170? So you would be inclined, based on your intuition, to reject the null hypothesis and go with the alternate hypothesis, right? That would be your intuition. But then some uh, of you may argue that, hey, this is just a sample, right? That this is just a sample. What if coincidentally, even though you selected this sample randomly, coincidentally you ended up selecting the grades or the classes with higher average height? What if, like, maybe this was 200, this was 180 average, right? Maybe these were inherently taller people and all the other grades just had average heights like this, so on and so forth. So then the overall average can still be 170, but these two sample sets are sort of outliers. So some sampling bias could have come in, even though sample is random. There could have been sampling bias because of random selection. So you could have ended up picking these two classes with a much higher height than the other classes, right? Hence, concluding that 190 is very high and it's unlikely that mu is equal to 170. And you have just picked a sample with more outliers or with much higher height than the school average. Right? This can be intuition for some other people, some of you, right? Okay. So now, of course, we can't go by intuition, right? Because we cannot do statistics based on intuition. What we need is a formal methodology to assess if the sample has yielded an average height of 190 centimeter. What are the chances that the population actually had a average height of 170, or what is the probability that with a population where this null hypothesis is considered to be true, where the average height is 170, what is the probability that you get a sample where the average height is 190 or more, right? What is the probability of getting such an outlier sample that you picked everyone from here, right? So this is your normal distribution, and now what we do is, in order to formalize this test, what we do is now assume h naught is true. So this is what your normal distribution can look like, where your mean is here, right? So what is the probability that you ended up picking this sample where the average, right, is 190 or more, right? If this possibility, if this probability, in fact, probability of getting a sample with a height of 190 or more, given that the null hypothesis is true, given that mu is in fact equal to 170, is very small. Let's say this probability, I'm just taking a hypothetical example, let's say this probability is only equal to 1%, right? If this probability is so small, if this is just equal to 1%, then what does this mean? It means that it's very unlikely to get this outlier sample. What are the odds that you ended up picking this 1% sample out of all the other possibilities, right? So it's very unlikely. So based on this, what you would end up saying is that mu is greater than 170, because see, you have gotten an average height of 190, right? That is the reality, but you don't really know if the null hypothesis is true. So that is what you are checking, right? If the chances of getting this sample of a height of more than 190, right, I've not taken equal to, I've taken greater than equal to, because you can't calculate probability at a point in a continuous distribution, right? So you will have to take a range. So I have said anything more extreme than this. So the probability of getting this sample or a sample more extreme than this, why is this more extreme? Because I'm going, so extreme means towards the alternate hypothesis, right? So alternate hypothesis is saying taller people, right? So is the alternate true or the null true, right? That's what we are testing, right? So the probability of getting a height of 190 or higher, given that null hypothesis was true, if it is just 1%, then it's unlikely that the null hypothesis was true. So the alternate has to be true. That is how you can go about it. But again, this is very conjecture based. What should this threshold be? That is a question, right? Should it be 1% or should it be 5% or should it be 10%? What is that probability that you consider low enough to reject the null hypothesis? Okay, so this is where the idea of p-value comes in. Okay, so now let's talk about p-value. What is p-value? P-value is the probability of getting this sample or getting the sample under consideration or a more extreme sample given that null hypothesis is true, right? What are you saying intuitively? You are saying what is the probability of getting this particular sample of with a mean of 190 or more given that null hypothesis was true. If this probability is too small, if it is too small, then we say that null hypothesis is not true because it is very unlikely, it is so unlikely to get a classroom with an average of 190 if the population average was 170 that I cannot believe that the null hypothesis is true, right? So what we are saying here is that it's so unlikely, very unlikely, that null hypothesis is true because you have gotten this sample. This sample is your reality, right? Null hypothesis I don't know about, right? So if given that this sample has come, if the probability of getting such a sample given that null hypothesis is true is so small, then it's very unlikely that the null hypothesis is true because this sample is definitely true. So we would reject null hypothesis. But on the other hand, if this probability is large enough, we can't reject the null hypothesis. So let's say there is a 15% chance or 20% chance that your sample mean could have been more than 190, right? Then you can't reject the null hypothesis really. You can't reject the null hypothesis because then you don't have enough evidence, right? Having enough evidence means that you have gotten a sample which is inconsistent with the null hypothesis, right? So a sample whose probability of occurring is very low is inconsistent with the null hypothesis. Okay, sample is inconsistent with H naught. So you can reject the null hypothesis. But if the probability of getting this particular sample is large enough, then it's not inconsistent with null hypothesis. It can happen even if the null hypothesis is true. So you can't reject null hypothesis based on this sample. This does not mean that null is false or alternative is true. It just means based on the evidence, you can't reject the null hypothesis. You need more evidence. And because null hypothesis is the status quo, because that is what we assume to begin with, we cannot reject it with this sample if the probability of getting this sample with the null hypothesis being true is large enough, if this sample is not inconsistent with the null hypothesis. Okay, so that is the intuition. Now how do you do it really? So the beautiful thing is that we know the distribution of x bar, right? So we can compute the probability that x bar is greater than equal to 190. So x bar has a normal distribution with mean as mu and variance as sigma square by n, right? So in this case, x bar has an approximately normal distribution with mean as mu, so that will be 170, right? And variance as so what is sigma square here? Sigma square is given as 900, right, by n. What is n? N is 80. right? So this is what we know. Now, what is the probability of getting this sample or a sample more extreme than this, right? So probability of x bar being greater than 190, what is the probability of this? That is what we are talking about. A sample which is, this is the sample we have gotten. Sample mean is 190, right? So what is the probability that x bar is can be 190 or more? It can just be calculated as probability that x bar minus mu divided by root over sigma square by n is greater than 190 minus 170 divided by root over 900 by 80. This quantity is called as the p-value. Okay, this is the p-value. This entire thing is equal to the p-value, right? Also, this quantity is called as the test statistic. Okay, so usually going forward, how we would do it is we would not start at x bar, we would start at the test statistic. Okay, this is a particular case when we are testing a hypothesis. This is just like confidence interval, right? So earlier we used to call this the pivotal quantity. Now this is the test statistic. Okay, so going forward, right, we would just say that x bar minus mu divided by sigma by root n is my test statistic. And this has a normal 0, 1 distribution, right? Because I have changed the origin and the scale, right? So I subtracted the mean and divided by the standard deviation. So now this quantity has a standard normal distribution, right? So this is the starting point usually, right? So now this is just the probability that z is greater than, this is 20 by root over 900 by 80, right? So now let's just compute this. So this is equal to 20 by 900 by 80. So this is equal to 5.96, right? So probability that z is greater than 5.96, right? Now what is this probability? Let's just go to the tables. See, we know this is anyway very large, so this will come out to be this is really outside the normal distribution practically, right? So but still let's calculate it. So now okay, so this is even larger than 0.999999. The CDF is even larger than 0.9999. That is the less than equal to probability. So the greater than equal to probability will actually be equal to, this will just be equal to 1 minus 0.999999. That it will keep on going. It will be a very large value, right? So the p-value would come out to be 0.00000001, right? Or something like that. We can't even know because 5.96 is not there in the tables, right? The last value you have is 4, right? At 4, the value is 0.99995 times, and then and before this you see like it's for 0.999999 for so long, right? So this is just like an extreme tail, right? So what does that mean? That means that it's very unlikely to get this class of students where the average height is 190. So your intuition was really correct, that 190 is very high. It's unlikely that mu is equal to 170, and thus we cannot reject the null hypothesis. Thus the null hypothesis is true. Okay, now this we have done intuitively, right? Let's think about it formally, right? So now what would this probability really have to be? What would this p-value? So this is your p-value, right? This is your p-value or probability value, which is the probability of getting a sample, right? Which is whatever sample you have gotten, or whatever sample mean in this case that you've gotten, this or a more extreme sample, right? uh, what is the probability of getting a sample like that? And that's the p-value, and that seems to be very unlikely, so we are able to reject the null hypothesis. Null hypothesis is definitely not true, because otherwise this would have never happened, right? Now to formalize, you don't directly reject looking at the p-value. You have to compare it against something. Okay, that is called as level of significance. So level of significance is basically the minimum p-value that is required to not reject the null hypothesis. That is, let's say this question said that the p-value is 5%. The level of significance is 5%. Okay, so in that case, if the p-value is greater than level of significance, that is 5% in this case, right, then this is the minimum value that is required to not reject the null hypothesis. So if this was greater than the level of significance, then we don't reject null hypothesis. Okay, and if the p-value is less than the level of significance, so it is not meeting that minimum threshold that we need, right? It is so unlikely that it's not acceptable to us, right? So such a sample cannot come, and thus we reject H naught, right? So that is the idea. That is how you go about hypothesis tests, right? That is the intuition. Now, as we progress further, we will discuss more and more questions. But in this video, I just wanted you to understand what is p-value. P-value is basically the probability of getting this sample, right, that we have gotten, or a sample that is even more extreme than this, right? And then if it is low enough, if it is lower than our level of significance, then you can say that we reject H naught, because this sample couldn't have come with null hypothesis being true, right? So that is the idea, right? Let's move on.